Have you ever considered how digital circuits manage to count and progress through a specific order of events? Imagine a system where each step naturally leads to the next, almost like a chain reaction, without a single central conductor directing every move at precisely the same instant. An asynchronous counter, also known as a ripple counter, sequences its states by using the output of one flip-flop to directly trigger the clock input of the very next flip-flop in its series. This creates a cascading or rippling effect, where the state changes propagate sequentially from one stage to the next. The fundamental reason for this behavior lies in its architecture. Each flip-flop typically operates in toggle mode, meaning its output changes state each time its clock input receives a falling or rising edge, depending on its design. Since the output of the preceding flip-flop becomes the clock for the subsequent one, the state transition of a later flip-flop is inherently delayed until the previous one has completed its own state change and produced the necessary clock edge. To visualize this, consider a simple 2-bit asynchronous counter. The first flip-flop receives the external clock signal, and its output then clocks the second flip-flop. When the external clock signal transitions, the first flip-flop changes state. Only after this change occurs will the second flip-flop receive its clock pulse and potentially change its own state, effectively counting through the sequence of 00, 01, 10, and 11. This sequential triggering introduces a characteristic known as propagation delay, which is the time it takes for the state change to ripple through all the flip-flops. While this makes asynchronous counters simpler to design and construct with fewer components, the accumulated delay can limit their maximum operating frequency and potentially lead to race conditions or glitches in complex, high-speed applications. Understanding the sequential, ripple-based operation of asynchronous counters provides a solid foundation for grasping how digital systems manage ordered processes. It highlights the clever simplicity of relying on internal state changes to drive subsequent actions, offering a practical and efficient method for basic counting tasks within digital logic designs.